In any distributed system, for efficient parallel processing and for better performance, the data distribution strategy and colocation of data plays an important role. I'm Arshad Ali, and in this video, in the context of Azure Synapse Analytics dedicated SQL pool, I'm going to walk you through data distribution strategy and best practices around it. But before we deep dive, let's quickly review architecture of Azure Synapse Analytics and more specifically SQL pool, which is based on massively parallel processing computing architecture. As I discussed in my last video, Azure Synapse Analytics is a limitless analytics service that brings together data integration, enterprise data warehousing, and big data analytics in a single, comprehensive, unified, and integrated service. As you can see in this architecture diagram, there are two types of analytical runtime that empowers the analytics in Azure Synapse Analytics. On the right side, we have Apache as Spark-based big data computing platform for big data workload, which we can do it with either Python, Scala, Java, .NET programming language. On the left side, we have SQL-based MPP engine, which allows us to write T-SQL commands for all types of analytical need, whether it's a batch processing, a stream processing, or interactive query. In this video, I'm going to get into details of dedicated SQL pool, what's the architecture behind it, and what's the strategy that we need to follow to distribute the data and make the performance optimal. This is the MPP architecture or massively parallel processing architecture that is behind a dedicated SQL pool. In this architecture, there are two types of primarily node. The control node, which works as a brain for the overall infrastructure, and the one and more compute node, which is kind of muscle, which does all the heavy lifting for your data processing need. User and application connects to control node and they submit their query. Control node takes that query, divides into or creates a distributed query execution plan, sends that query execution plan to all the compute nodes in the database, and all these compute nodes work independently in parallel, processes the data and sends the response back to control node. Control node aggregates the data and send it back to application and user. For the data movement between compute nodes and between compute node and control node, there is a service called DMS that does that work. As we store the data into any table in dedicated SQL pool, the data gets broken down into multiple buckets and gets stored. There are 60 buckets, which in context of dedicated SQL pool is called as distribution. And depending on the number of compute node that you have in the database, those distribution get assigned to those compute node. So consider a scenario where you have one compute node and the data is distributed across 60 distribution, and all this distribution get assigned to the single compute node. Now consider another scenario where you have two compute nodes. Again, we still have 60 distribution where the data is distributed. Now because we have two compute node, the number of distribution get assigned to each of this compute node will be half of 60. Basically 30 is getting assigned to compute node 1 and 30 getting assigned to compute node 2. So in that case, each of this compute node will be kind of processing roughly half of the data which is there in the table. If we change the configuration and add one more to this database, right? So in this case, because again we have 60 distribution, the number of distribution equally gets assigned to each of these compute nodes. So in this case, 20 of this distribution will be assigned or attached to compute node 1, another 20 to compute node 2, and finally last 20 to compute node 3. So 1/3 of the data will be processed by compute node 1, 1/3 by another compute node, and finally the last 1/3 of the data will be processed by the third compute node. And this is how it scales to, say, if we have 4 compute node, right? So in this case, like 15 of the distribution will get assigned, and roughly 25% of data will be processed by one compute node in parallel to the other three that we have in this infrastructure. And this is how we can keep on scaling the number of compute nodes to create more parallelism to execute our query. This is another example where we have 5 compute nodes. So again, given we have 60 distribution, each of those 5 nodes gets 12 distribution assigned to them to process the data for that table. This is how we can keep on scaling our computing infrastructure behind dedicated SQL pool from all the way from 1 compute node to 60 compute node, given that we have 60 distribution in this case. So this is where we keep on scaling it up, but that's not the only way you can go. When you do not have requirement of that much compute resources, you can scale it down. So you can come from, say, compute node 5 to 3 to 2, based on if your requirement is reducing for processing, you want to optimize the cost, you can scale it down to have lower number of compute node. As well as you can pause the resources if you have off-peak hour when you do not need any computing resources, you can pause the resources to release all this computing infrastructure and only pay for the storage during that time. This is how it looks like. When you pause the compute infrastructure or the database, all the compute resources will be released and you'll be only paying for the storage during that time as long as you have paused database. Once you need it back, you can resume and you have the compute available in a minute or two for you to start working on that. So this is how we see that the data gets distributed across 60 distribution in dedicated SQL pool. After looking at how the data gets distributed across 60 distribution, now the question is how SQL engine knows that what data to store in which distribution. And this is where distribution type and the table type discussion comes in play. So when we talk about distributed table, there are 2 different types of table that we can create. The very first one is round robin. Round robin distribution is the default if no options are used in create table command. The data will be spread evenly over 60 distribution that we have in the database for each of the table. Whereas has distributed uses a deterministic has function to determine on which distribution a particular row should be stored. These 2 different distributed types of table are largely suited for large tables. There is another third one called replicated table. Replicated tables are copied to each of the compute node, and we will look into the details of it. And finally, the fourth type of tables is the external table, which is part of the polybase feature, which allows you to kind of ingest the data just by creating the external table and loading the data into internal table via the external table. A round robin distributed table distributes table rows evenly across all the distribution. The assignment of rows to a distribution is random. Unlike has distributed table, which we'll discuss next, rows with equal values are not guaranteed to be assigned to the same distribution. As a result, the system sometimes needs to invoke a data movement operation to better organize your data before it can resolve a query. This extra step can slow down your query. Let's see how the data gets stored into a round robin distributed table. We have this incoming data coming in, and as you can see, the data gets first stored into 18, 19, 28 distribution. Next time the data, when it comes in, it can go and can be stored in any of the distribution just to make the data is evenly distributed across all this distribution. And this is how it keeps on going. Now let's look at one practical examples of how it gets stored. Let's say we have this data on the left side which we need to store into a round robin table, and this is a data for transaction table, and what we see here is 111 or 222 or 333. These are product key, and for each of the product key there are other information like transaction ID, transaction date, and all those things which are not relevant for this discussion, but consider for each of this product being sold, the amount is provided over here. Now we are going to store this data into a round robin table. When we do that in a dedicated SQL pool, the data would be stored in randomly and will be ensured that the data is evenly distributed. So once the data is stored into a round robin table, this is how it should look like. What we see here is this is a 4 compute node SQL database. It means like there will be 15 distribution assigned to each of the compute node, and what we see here is the data is kind of evenly distributed across all this distribution which have been assigned to different compute node that we see over here. Now if you want to run a query like this, right, so we want to query from this table and want to do a group by on product key and do a sum of all the amount that we have. Because the data is not stored for all the product key at one location, there is no colocation here, it would require the data shuffle so that the data for a particular product key is available at one location for it to do the aggregation. And this is where data shuffling comes into play based on the query that we are writing. This can be minimized with the hash distributed table, and that is the intent, and that is something that we'll look into the next part of this discussion. But note that round robin table requires data shuffling. This data shuffling is not very bad, given that the networking infrastructure that is kind of used behind the scene here is highly performant. It should be fine in most of the cases if it does the data shuffling. However, we try to get into a situation where it doesn't have to do the data shuffling, and how we do that is going to be discussing next with distributed hash table. At this point of time, because the data is collocated for each of the product key, it can do aggregation of each of the product key and generate something like that. This aggregated data is sent back to control node via data movement service, and control nodes returns the results back to the end user. This is round robin table. This data movement, as we were discussing, or the data shuffling between compute node that we were discussing earlier, can be minimized if we choose a right hash distribution key for a hash distributed table. But before that, let's see how does it work. Let's say we have this 01 as a value, hash distributed key value is coming in, and that data gets stored into one of the distribution. In this case, it's a 05, right? Next, another value is coming called 02. That data gets stored into 31 distribution. Then finally 03 is coming in, and that gets stored into 46 distribution. 01 coming again, and because it uses deterministic hash function, that data will always go to 05 distribution, and so forth. So basically, a hash distributed table distribute table rows across compute nodes by using a deterministic hash function to assign each row to a particular distribution. Since identical values always hash to the same distribution, SQL engine has built-in knowledge of the row locations, and this knowledge is used to minimize the data movement during queries, which improves query performance. This is another representation of how the data gets stored into a distributed hash table. This is coming from the official documentation for hash distributed table, and what you see here on the left side is the data that's coming to be ingested into the table, and we have a hash deterministic hash function in between with which we define the distribution key, and using that distribution key, that function distribute the data in the different distribution that we have here. Let's take the same example that we had earlier with the round robin and see how does it work with distributed table, where we have a hash key identified and table is distributed on that hash key. So we have the same data coming in again, and now what we are going to do is we are going to create a hash table distributed on product key. And once we do that, we can ingest the data into this distributed hash table, and then this is how it should look like. Because it uses this deterministic hash function, for each of the product key, the data is going to be in the same distribution. So this colocation ensures that when you run the same query which you ran earlier, it doesn't require any data shuffle because of this data colocation. So for 333, it's all going to be in one distribution. Likewise for 222, it's going to be in another distribution. 111, it's going to be another distribution, right? So given this is all together at one location for a particular product key, the group by can be performed without doing any shuffling of the data here in this case. It does again the summation by doing the group by and results in sent back to control node via DMS, and control node sends it back to end users, and again this is going to be the same result. With that, it's time to look at some practical examples of how it's going to look like. Before we get into practical examples of how data distribution strategy works and how the data gets distributed in each of those strategy, let me show you first what's the size of the database that I have. So if I go to my Synapse workspace in Azure portal, I can see all the SQL pools created in this workspace. I have this one Synapse Learn Synapse DB, which is a kind of dedicated SQL pool, and the size for this database is DW1000C. With that, let's go to another page where we have the official documentation about different performance level, and with DW1000C we see that there are 2 compute nodes, right? And since we have 60 distribution, each of those compute node will have 30 distribution assigned to it or attached to it. So basically one compute node will process 50% of the data of the table, right? So this is what you see as a 30 for the number of distribution assigned to per compute node. There are a couple of things to note here. The very first thing is, with every 500 DWC increase, you'll see one new compute node added to the infrastructure. So for example, for 1000C, we have 2 compute nodes. For 1500C, we have 3 compute nodes. For 2000, we have 4 compute nodes. This goes all the way from 100C or 500C, where we have the 1 compute node with the maximum memory available, all the way to DW30000C. In this case, we have 60 compute nodes, and because we have 60 distribution as well, each of those compute node gets assigned 1 distribution to work at that point of time. So this is the maximum parallel processing that we can achieve. Now if you are wondering why 60 distribution, so Azure Synapse Analytics team has kind of identified 60 distribution as an optimal level of distribution for hundreds of terabytes to petabyte of data processing scale. For example, if we talk about 600 terabytes of data warehouse at DW30000C, in that case, like each of the compute node gets to process 10 terabytes of data. So this is one point to note from here. The other thing is, if you look at the number of compute node, right? So it goes all the way from 1, 2, 3, 4, 5, 6, and then it goes to 10. And the reason is the number of compute node in the infrastructure should be the factor of 60, so that each of the compute node has equal number of distribution to work on. Say for example, if we take an example of 8 compute node, and if we divide 60 by 8, it will not give the even number of distribution for each of the compute node to work on. That's where you see the number of compute nodes we can scale up to is the factor of 60, right? So this is 6, and then it goes to 10, 12, 15, 20, 30, and 60. Now let's look at this on SQL side. Let me go to SQL Server Management Studio, and there are certain system views which provides the information about all the metadata that SQL pool has stored. And the very first one is sys.dm_ptw_nodes. So this is the system views which is going to give us the number of nodes that we have for this database allocated, right? If I execute this, you'll see there are 3 nodes over here. The very first one is the control node, and the other 2 are compute node, right? So the point to note from here is the ID that has been assigned randomly here, and it gets assigned when we are kind of restarting a paused database or when we are creating a new database, right? So in this case, it's 31 and 57. So note this number, and we'll look at that in the next script. In order to get the number of distribution that we have in this database, we have another system views called ptw_distribution. If we execute this command, this is going to give us all the distribution that we have in the database. In this case, it's going to be 60, right? So it's going to be from all the way from 1 to 60, as you can see here on the bottom, right? And as I talked earlier, because we have 2 compute node, one of the compute node will have 30 distribution assigned to it. And this is something that we can look at here and confirm, right? So if you see here, distribution ID 1 till 30, they all have been assigned to node ID 57. So this node ID 57 is the one of the node ID for the compute node. Likewise, if we go from distribution 31 all the way to 60, if you see this, all these distribution have been assigned to node ID 31, which is another compute node. So this is about the distribution and how this distribution have been kind of assigned to each of the compute node equally so that they can process the data equally during the processing. Now, let's go to the next step, and what I'm going to do in the next step is I'm going to use the Contoso sample database that has been provided and provided by Azure Synapse Analytics team, and use that as an example to show the different data distribution strategy. I'm going to provide you the link how you can install and set up Contoso database in the description, as well as I'm going to also provide you the link where you can download all this script which I'm going to demonstrate in this example. So the very first thing is I'm going to create a table called fact online sales. This is an external table, right? So it's a part of the Polybase feature which allows us to create a table based on the data file sitting on the data lake store, right? So I'm going to create this external table with definition that I have here. This is the location where I have the files, and this is the data source where those files are sitting, and this is the file format it's going to use to kind of read the data from that file. So I'll not get into details of Polybase right now. I'll keep that for next session, but let's go ahead and create this external table. So command is executed and external table is created. In the next script, I'm going to create 2 internal tables. One internal table is going to be round robin distributed, and this is what we see. So I'm saying create table, and absence of external means we are creating an internal table, and this is the name of the table that we are creating with distribution equal to round robin. So in this case, the table is going to be created as round robin, and then I'm selecting from the external table that I created earlier in the script, And then this is an optional level which we can attach to the query that we are executing. This is not required, but if there are multiple users working together and you want to analyze and find out the query that you are executing and analyze it, this level comes in play. Right? So this is an optional level that you can specify for your query to do the analysis later. I have put it here. And the next table is going to be fact online sales hash table, and I'm doing the distribution here using the hash key or product key. Right? So this is hash distributed table on product key, and the source is going to be the same source that we used earlier in this table creation, right? So in this case, there will be two tables created. Both will have same set of data, but one will be round robin distributed, and the other will be hash distributed on the product key. Let me execute this script to create those tables and load the data into those tables. While it's coming up, it might take a couple of seconds to a couple of minutes based on the data volume that we are trying to ingest into those internal tables, as well as the performance level that we have selected for the database that we have. In our case, I have selected it to be 1000 TWC, where we have 2 compute node, and then finally the user account I'm using, to what resource class that user account belongs to, right? That determines the amount of resources allocated to that user account when the user is executing some query. That comes under as part of workload management and concurrency, which I'll cover it in my next video. So these two tables are created. Let's go back here. These two tables are created, and what we generally do, and this is kind of a best practice, is once we create a new table or we load large volume of data in a table, we kind of go ahead and create a statistics manually right after that for better performance of your queries. Synapse Analytics or dedicated pool in particular, it allows you to kind of set up a configurable parameter where it creates statistics or update the statistics based on the query pattern that you are executing. But in this case, it's recommended once you load the data, you create the statistics beforehand, or you update the statistics beforehand, type of taking a proactive measure instead of doing a reactive taking a reactive path here. So this is done. These two tables are created, and now what I'm going to do is I'm going to use this view to query some of the data for each of this table. The script to create this view is available on this link, which I'm going to post it as part of this script, and you can use that to create for yourself. And what I'm going to do is I'm going to query this view and pass the name of the table that I just created, and list some of the columns that this view has. Right? Let me run this and show you the result. Like I said earlier, each table that we create, there are 60 internal tables getting created, and each of this internal table will belong to each of the distribution that SQL pool has, right? So we created this table, and as you can see, this is my table name, and these are internal tables name that have been created for my table that I just created, right? And the distribution type is round robin for this specific table. And what you also see is row count in each of the distribution. And what you'll see is the number of row counts are very similar to each other. And this is because that SQL pool ensures that data gets distributed as evenly as possible across all this distribution. And you'll also notice that we didn't specifically specify the index type on this table, but because the cluster column store index is the default, cluster column store index has been created on this table. There are certain other columns which give some additional information. For example, amount of reserved space in GB allocated for this table or for this distribution of this table. Likewise, unused space. data space used, index space used, right? So these are per distribution. If you want to get the kind of consolidated amount of space used, you can do a group by and you can do a sum of all these values to get the consolidated space allocated, used, and index used for those, that is that table. So this is for round robin table. Let's go ahead and let's run the next script, and in this script it's the same as the earlier one. The only difference we have here is the table name that we are passing is the name of the table, which is kind of created as a distributed table on product key. And if we can query this table, run this query, you will see that this is my hash table, right? And these are all the distribution of that hash table, 60 distribution. That is what you can see here on the bottom, 60 rows coming up here. And this is going to be the hash distributed, right? This is hash, indicates the hash distributed, and distribution column is the product key, which we use to do the hashing when we are distributing the data. What you will again notice over here is the number of row count in each of the distribution, and this could vary from how much distinct value you have for that specific distribution column. Ideally, it is recommended to kind of choose a distribution column which has large number of distinct value. At least it should be larger than 60, because 60 is the total distribution that we have. As large as it is, you'll see as close as it is to have even distribution of the data. Here, because the data volume is not that huge, you see some gap over here. But if we are talking about a table with billions of rows, the difference would be very minuscule if the selected distribution column has large value of distinct, large number of distinct values. So this is about row count, and again the default index here is again clustered column and store index, and all these columns are again as same as the previous one. So this has distributed on product key. Let's go to the next one. In the next script, what I'm going to do is I'm going to run the same script on both these tables that I have created, right? So in this case, if you can see, I'm selecting product key and doing a sum on sales amount, selecting from round robin table that I have created, and doing a group by and order by on product key, right? So this is one query, and I have another query which is exactly same as the previous one. The only difference this time is my source table has distributed table. If I go ahead and execute this script, what I'm going to get is the exactly same result set, right? So in the first result set, if you see here, we have got 2516 record, 2516 record. Likewise, in the second with the second script also, we have got the same number of rows with the same set of values, right? So this is giving us exactly same result. However, how it's getting executed differs because of the distribution that we have selected, and let's see that. Next, let's select this query again and look at the different execution plan being created for this queries, right? And to do that, select the queries and click on display estimated execution plan icon in this SQL Server Management Studio. This is going to give us the execution plan for both of the queries. In the first query, if you see here, most of the time which is being taken is the shuffle operator, right? So shuffle operator is taking 100% of the time because we are doing group by on product key, and since product key is kind of randomly distributed across all the distribution, and in order to kind of serve this request, engine has to bring all the same product key at one location. So basically it has to do some collocation of data so that it can generate the aggregation for that data. And to do that, it uses a shuffle operator, and this, in this case, as you can see, it's taking almost close to 100% of the overall time it's taking to execute this whole query. In comparison with that, if you go to the second query, which is again providing the same set of result, it's because we do not have shuffle operator in this case, as we do not need it, because our query is doing a group by on product key and the table is distributed on product key. It doesn't need to do data shuffle. That shuffle is not needed here, and it's serving the request by simply doing the aggregation and doing the sending it back to the end user, right? So this is how the simplified query it's going to be if we do right distribution of the data, right? So this is execution plan. You can also use explain keyword to look at the execution plan being generated for this queries, right? So if I go ahead and execute this, but before that, let me explain you that this is the query that I have earlier, and now what I'm doing is, before this query, I'm simply adding explain keyword for the query 1, and same for query 2, right? If I execute this, it's going to give me the execution plan, distributed execution plan, which we talked about earlier for both of these queries. So this is for query 1, where we are using round robin. Let me copy this XML data which has the query execution plan, copy it here, and let me also take the execution plan for the second query, which is leveraging has distributed table. Now if I go here and paste the execution plan for the second table, you see this plan is very simple, and the only operator being used here is to return the data by doing the aggregation, local aggregation of the data as it's co-located, and query executing much faster. Unlike the other case where we have data shuffle, and this is what you see. So before it executes the query, it needs to do the data shuffle, and this shuffle itself is taking this much amount of time, and this time is as much as the total time it's taking to execute the overall query. So basically, like we can say, the time taken to do the shuffle is close to 100% of the time it's taking to execute the query itself. So this is because of the shuffle operation. Now let's go back here again in the SQL Server Management Studio. Let's go to the query that we have here and execute this query one more time. And the reason I want to execute this query one more time is I want to show you another way how you can look at how these queries are getting executed, right? So to do that, let's go to Azure Synapse Studio. So this is Azure Synapse Studio, and on the left side you'll see there is a tab for monitoring the workload that's running on this workspace, right? Click on this tab and then go to SQL request, right? So because we are running SQL workload for now, let's click on the SQL workload and then come here and hit refresh, and this will show you all the query that has been executed in last 24 hours. If you are not able to see any data coming up over here, it could be probably because these filters are not correct. Most probably you have not chosen the right SQL pool. You have to choose the right SQL pool against which you are running the query, and once that is done, you'll start seeing the data coming up over here, right? So I executed these two queries, and this is what I see. Query ID 5400 and query ID 5401. Let me click on 400 or 5400 here, and let's open another window where I'm going to kind of open the next one, 401, and let's analyze the difference. So in this case 401, right, to look at the query that was executed as part of this execution, we can click on request content, and if we go here, it's going to show us the query that has been executed as part of this execution, right? So we are selecting this product key, doing the aggregation on sales amount from the has table, and then we are doing the group by and order by on this table. And what we see over here is there is only one operation type to return the data, doing the aggregation and returning the data back to end user, and it's going to take 234 milliseconds to do the execution, and total number of record return is being 2560, right? So this is very simple execution without involving much overhead. Let me go back to the previous one. And in this case, if we look at the query that has been executed as part of this query, we can click on request content, and you can see we are selecting again the same product key and doing the sum of sales amount. However, this time we are selecting from the round robin table and doing the group by on product key and doing the order by on the same product key. In this case, because the data is not co-located, it needs to do a shuffle operation, and this is what we see, this shuffle operation type. If we go on to the right side of this, you'll see that most of the time for execution has been taken by this shuffle operation itself, right? And finally 2516 record has been returned by this return operator. From here again, you can click on export query plan, and it's going to give you the same XML which we saw earlier in SQL Server Management Studio. If I open this, you'll see the execution plan XML, the distributed execution plan, and you'll see the same shuffle move here because of the shuffle move involved with round robin table. And if we go back again to the other query where we are running this on distributed table, export query plan, and look at the query plan, you will notice that we do not have shuffle operation. It's just a return operation which returns the aggregated data which is co-located and runs much faster. With this, we can say that choosing the right distribution strategy makes difference here, and we need to kind of be careful when we are kind of choosing the distribution strategy and define table, especially the large table as has distributed based on the query pattern that we are seeing. With that, let's go back again to SQL Server Management Studio, and this time look at a different scenario. So far we looked at a query which is based on a single table. But what if there are multiple tables involved in the query execution, right? I'm going to take an example where we have two tables and I'm joining these two tables together. However, the same concept applies even if we have more than two tables, right? So to do that, let's first create another table called dim product. So we have fact table. Now let's create another table called dim product. This is going to be an external table, and to do that, I'm going to simply execute this script. After execution, we can see our external table has been created. Now let's go to the next script, and what I'm going to do with the next script is basically from this external table, I'm going to create two tables or two has distributed dimension table, right? The first table is going to be dim product, and it's going to be distributed on product key, and this is how I have defined the distribution. Distribution is equal to has, and it's going to be on the product key. The second table is going to be again a distributed table, but this time the distribution is going to be on a different table, different column, right? So this is my two tables getting created. What I'm also going to do is create a dimension table based on round robin, and I'll show you different behavior based on the different types of distribution that we are using. And even for the distributed table, when we are using different columns and those columns are being used in join, how does it work is something I'm going to demonstrate next. So let's take the next query, and in this case what I'm going to do is I have this fact online sales has table which is kind of distributed on product key. I have another table, this is my dimension table, and this table is again distributed on product key, and I'm doing a join on product key from both sides and doing a group by and doing the sum and getting the product key. So this is one scenario where we have join compatibility for joining keys that we have in this query. There is another scenario where we have these two tables. The very first one is has distributed on product key, and the dimension is has distributed, but it's distributed in a different column, not on the same column as the fact table, right? So in this case, this join is incompatible, right? So let's execute this two query again. These two queries are going to return the same set of data. However, how it gets executed differs because of the distribution strategy that we have used for the underlying source table. With that, let's switch back to Synapse Studio again to look at the execution plan for each of this query. Let's go there, refresh it here again, and let's look at the joining of this table. Click on this query. This is 5457, and the request content for this query is what we executed here. So we have one has distributed table, and then we have another table which is again has distributed, but it is on a different column. So we have here join incompatible joining keys, right? And that has caused a shuffle of data for this query to get executed, and this is what we can see in the request state. So if we go here, we can see that there is a shuffle move operation for one of the table data to kind of move the data or collocate the data to do the aggregation on the data set, right? And SQL pool is smart enough to figure out that out of these two tables, one is the bigger fact table and the other one is smaller dimension table. So it has done the shuffle move of the data for the smaller table, and this is what you can see. Total number of rows in that dimension table is 2570, right? So this way it's doing shuffle move because of incompatible join. However, it is trying to optimize the move by picking the smaller of those two tables. If we go to the next query that we have, where we have join compatibility between joining keys, we can see the query again by going to request content, and what we are doing here again is same query. However, this time we have has distributed on product key, and then we have a dimension table which is again has distributed on product key, and then with that we can say that we have join compatible joining key or kind of distribution column here. And because of that, for each of the product key, data is co-located. It doesn't need to move the data across nodes to do the processing, and because of that, it simply needs to do the local aggregation and send the result back. And this is why we see that only one operation in this case, return operation by doing the local aggregation of the data, because the data is locally co-located, and then returning back the result to the end user. So with that, we can see that how joining column are important when we are deciding what should be the right distribution column to distribute the table on. With that, let me give you another example of data skewness. Let's go back to SQL Server Management Studio, and let's go to this example. What I'm going to do this time is I'm going to create the same fact table, and going to do the distribution on a store key. And in my data, I have only 3 store key. So basically what does it mean is there will be only 3 distribution where all the data will get stored. And let's look at that, right? So I'm going to execute this script and it's going to create the table. And then while it's running, let me kind of talk about the next query that we have. Again, the same query as the previous one. Again, I'm querying the same view, sending the name of the table that we just created over here, and running this query just to see how the data has been distributed across all those 60 distribution. And as we were guessing, you can see that all this distribution from 1 to 15, they are all having 0 rows. There is one distribution where we have this data. There is another distribution where we have this data. And there is the third distribution where we have the data. And that is because we have 3 unique store key, and 3 distribution have got the data for those unique store key. So this is how the data skewness comes in play. So when we decide, when we are picking up a right distribution key for the table, we also need to ensure that the table or the values in that specific column has higher number of unique value, or at least it should be higher than 60 unique value. With that, let's go back to the slide again and let's review what we have learned about different distribution strategy and do a summary of each of the learning that we have so far. Now let's recap what we have learned so far about round-robin distributed tables. It distributes table rows evenly across all the distribution. Rows with equal values are not guaranteed to be assigned to the same distribution. It means there could be a data movement when we are kind of doing the aggregation on the data. That will require the data shuffle, and there will be a data movement with that. You should consider using round-robin distribution for your table in the following scenarios. The very first one is when you are getting started and you don't know what is the right distribution key for your table. When you have multiple queries and all those queries are based on different joining key, and you don't have a very obvious joining key to kind of consider when you are deciding the distribution column for the table. When there is not good candidate column for hash distributing the table, and if table does not share a common joining key with the other table, if the join is less significant than other joins in the query, right? And you use this round robin table mostly on the staging table, right? So when we talk about data warehousing scenario, we have ELT and we have ETL type of data load pattern. And mostly when we talk about MPP engine, we use ELT. We extract the data, load the data into a staging table and do the transformation. So when we are loading the data into a staging table, those staging table could be round robin table to start with. Next, hash distributed table. It uses hash function, which is kind of deterministic in nature, which is used to assign each row to one specific distribution. With this, identical values always has to the same distribution, so it has the data colocation. Distribution column should have even distribution of values, right? So when we are deciding or picking up the column to do the distribution on, we have to see it has large number of distinct value for that specific column values. Hash distributed table works well for large fact tables. Consider using a hash distributed table when the table size on the disk is more than 2 gig compressed, and when the table has frequent insert, update and delete operation. With respect to selecting right distribution column, these are some of the best practices that you can follow to kind of identify what's a right distribution key column. For a large fact tables, best option is to have distributed distribution strategy. With that, all of the distribution should have approximately the same number of rows. Distribution on the column that is joined to other fact tables. So that is the column which has which makes the ideal candidate for distributing the data on. And often it could be your primary key or surrogate key in the fact table. However, be mindful of hash column should have highly distinct value, high number of distinct value. At least it should be as low as 60. Avoid distributing on a date column. So date column is often used in filter condition, right? So you should avoid using it in a you should avoid using date column to do the distribution on, because if you use the filter, some of the data from some of the distribution will be kind of excluded, and only few of the distribution which has the data based on your filter pattern will be kind of processing your data. So not all the compute resources will be utilized in a parallel fashion. So you should not using a column or any column which is being used in a filter condition. Avoid distributing in a column with high frequency of null values or default values like -1, which we use in case where we have missing dimension record. And this is because that all the null values all the values with -1, they all land into a same distribution. So think of a scenario where you have a table with, like, say 90% of null values or 90% of -1. In that case, your 90% of the data is landing into a single distribution, and rest other are kind of having rest 59 are having 10% of the data, which is not the ideal situation here, right? So you should avoid using distribution column on a column with high frequency of null values. If it is nominal, I think it should be acceptable, but it should not be very high. And know that distribution column is not updatable. Updates to data in the distribution column could result in data shuffle operation. For compatible joins, use the same data types for two distributed tables, right? So we saw that in the example earlier. We had two tables, and both of these tables are distributed on product key, right? So that is the value being used to kind of do the join between these two tables. The key column or the value of the column is important to do the join. However, also important is the data type of this column. So both sides, it should be the same data type. If one side it is int and other side it is big int, that's not compatible join. In that case, you have to make it of the same data type. Either make it big int both side or make int on the both side. Now, the one thing that we have to keep in mind that when we are choosing a distribution column, you have to think how we can minimize the data movement. And as we know, data movements commonly happens when queries have joins and aggregation. So ideally, your distribution column or distribution keys should be on the column which are being used in join, group by, distinct, over, or having clause. It should not be on any column which is being used in the where condition or filter condition. We just talked about date and how it can be filtered out to only have the unbalanced data for processing. If there are no distribution columns that make sense, then you should use round robin as the last resort. With that, we can conclude our discussion on different distributed table like round robin and hash distributed table, and switch to replicated table, which is the third type of table that we can create in SQL pool. A replicated table has full copy of the data on each compute node. And how does it work? SQL pool implements a replicated table by maintaining a master version of the table. It copies the master version of the first distribution database on each compute node. When there is a change, the master version is updated first, and then the tables on each of the compute node are rebuilt. A rebuild of a replicated table includes copying the table data to each of the compute node and then building the indexes. Replicating a table removes the need to transfer the data among compute nodes before join or aggregation, and this makes sense for majority of your dimension table which are very small in size. Roughly, if the size of the table is 2 gigs compressed, you should consider it creating as a replicated table. However, that's not a hard limit. If the data is static and does not change very frequently, you can replicate even larger tables and you'll see better query performance. Replicated tables may not yield the best query performance when the table has frequent insert, update and delete operation, right? So dimension tables are supposed to be updated infrequently, right? If the data is getting updated very frequently, replicated table might not be the right solution. This DML and that is because this DML operation require a rebuild of replicated table on each of the compute node every time there is a change in the data. And this rebuilding frequently can cause slower performance. The data warehouse is scaled frequently, right? So if I have the database which is of size 1000 DWC, and if I scale it to say DW 2000C and scaling up or scaling down, if I'm doing it so frequently, it needs to rebuild this replicated table on those new compute node very frequently, and it will slow down the performance. So if I'm doing scaling of the database very frequently, replicated table would not be a right fit there. And when the table has a large number of columns and the data operation typically access only a small number of columns. This is one representation of how data gets stored into different compute node, right? This is from the official documentation, and the link for this documentation is provided over here. And what we see over here is when the data comes in, all the data for that table is being copied to the all the compute node in the infrastructure in the database. Like I said earlier, for large fact tables, hash distributed table is the right way to go. If we cannot figure it out, the right distribution key, then round robin is the way to go. So that's about large fact table. Now when it comes to dimension table, if the dimension table is very small in size, where we have like say less than 2 gigs of data, or it has less than 60 million of rows, we can consider it creating as a replicated tables or round robin table with cluster index. If the dimension table is large enough, or it is large, you can treat it as a fact table and you can create it as a distributed table on the key which is being used in the join. With that, let me show you some examples and go back to SQL Server Management Studio. Earlier I created a dimension table which is kind of round robin distributed, and I created another fact table which is again round robin distributed. What happens if I have a query joining these two tables together, right? On any of the column from these two table, it doesn't matter because we are not talking about hash distributed table here. So if I execute this query, let me run it, and once this comes back, this is going to give us the same result set as earlier. So here we are in Synapse Studio again, and if we can click on the last query that we just executed and look at its execution plan or distributed execution plan. Let's first look at the query that was executed as part of this execution, And this is what we see. We have one round robin distributed fact table and round robin distributed dimension table joining on this product key and providing the same result set. However, the distributed execution plan has several steps involved here. And one of the data movement operation is for shuffle move, and this is for your fact table, right? And this is what you see, right? The number of rows being moved across is this much. And what we also see apart from shuffle move is broadcast move operation. So SQL pool or SQL engine is smart enough to know that in this join of two tables, one table is very small, and the data for the small table can be broadcasted, and it's using the broadcast move operator to move the data across for joining it with the fact table, right? And this dimension table has very less number of rows that you can see over here. So what we see here in this case is like basically there are two operator which is kind of doing or taking much of the time during the execution, right? And we can optimize this by making the other distributed table, or basically the dimension table, which is kind of distributed as a round robin table. We can make it as a replicated table so that the data for that table is available on each of the compute node, and with that we can get rid of broadcast move operator that we see over here. To do that, let's go back to SQL Server Management Studio one more time and create a replicated table. So what we are doing here is I'm saying create table, name of the table, and distribution this time is replicate instead of round robin. And again, the source for the table is the same source which we used earlier, and I'm going to create this replicated table. Let me execute this. Next, I'm going to execute this command. This command is simply selecting one of the record from that replicated table, and this triggers a rebuild of this replicated table. So in this case, the copy of data for this replicated table will be copied to all of the compute nodes. So let me execute this. This is going to be executing much faster because the first execution is anyway coming from the master version of the data. Now next, what I'm going to do is I'm going to run the same query as previous one, but this time I'm going to use the dimension table which is kind of replicated, and the fact table remains as is from the previous one. If I execute this and go back to Synapse Studio, we can select the query that we just executed and look at its query content, and this is what we see. So we have this fact table which is kind of distributed as a round robin, and then we have a dimension table which is a replicated dimension table. So in this case, it just needs to do the shuffle for fact table, and because the data for the dimension is already available on each of the compute node, it doesn't need broadcast as earlier, and that is something that you see not available here. So this way, by just making a table from round robin distributed to replicate, we are optimizing the performance. So this is how you can make your smaller dimension table as a replicated table and get rid of broadcast move that we saw earlier. So in this scenario, we have one round robin distributed table and one replicated dimension table, and we see shuffle move operator as expected. However, what we can also do is we can create the fact table as distributed table on the column which we are using as a joining key, and see how it works, right? For that, let's go back to SQL Server Management Studio and look at the next query that we have. So in this query, it's the same query as the previous one. However, this time I'm using the fact table, which is kind of hash distributed on product key. And then I have another table. This is a dimension table. This is again, I created it as a distributed table on same joining key. And this is my query 1. Query 2 is basically I have the same fact table, which is kind of hash distributed on product key. And then I have dimension table, which is the replicated one. Now let me execute these two queries and let's see how it's getting executed underneath. For that, let's go back to Synapse Studio. We'll go here. So here we are in Synapse Studio. Let's look at these two queries that we just executed and their execution plan. If we go to query 583 and look at the query that was executed, we have hash distributed fact table, and then we have hash distributed dimension table on the same key which are being used in the join product key. And what we see here, because of data colocation, it doesn't need to move any data, and we just see the return operation by doing the local aggregation of the data and sending it back to end user. So this is query 1. If we go to query 2, where we have same fact table, which is kind of distributed on product key, and then we have the replicated dimension table, right? If we look at its execution plan, it still has the same return operation, and the reason is, even though the distributed table is kind of the fact table is distributed on product key, and we are doing the join with the product key on the other side with dimension table, the dimension table data is replicated on each of the node, and that doesn't require engine to move the data across compute node. And because of that, what we see here is only the return operation, which does the local aggregation of the data, join and aggregation of the data, and sends the result back. This has been a long video which covered very important topic when working with dedicated SQL pool. I talked about data distribution by way of distribution, different data strategy like round robin and hash, and finally replicated table. I also talked and provided guidelines in terms of when to use which and what are the considerations for better performance. Thank you for watching. Hope this was informative for you. In my next video, I am going to talk in detail about column store index and how it helps in improving performance for analytical queries. Stay tuned.